screen real quick. Can everyone see it?
Yes.
Okay. Okay. So dynamic programming is a technique used in programming, and the basic gist of it is to find a base case and dimensions of dynamic programming, and then find transitions between different states of the dynamic programming, and then calculate all the states, and then you find the state that is the answer. I'll first go over a classic problem of dynamic programming that should demonstrate how it works. So knapsack problems are a classic example of a dynamic programming problem, and they involve filling a container with a subset of items, and we want to optimize some quantity associated with the items. So basically each item has a positive weight, and the total weight of the items we choose must not exceed the container, the capacity of the container. And so here's an example of a classic knapsack dynamic programming problem. Here's a statement. You want to find how many sequences of dice rolls exist such that the sum of the top faces is n, and n is less than or equal to 1 million. And so the constraint really isn't that important here, but basically it allows us to do a linear time solution, and the solution is here. We have an infinite number of items of weights 1 through 6, which represents all the different possible dice rolls, and we want to count how many sequence of items exist such that if we put the items into the container while following the sequence, the container becomes completely full. And the container is, in this scenario, is simply n, is a figurative container of size n, and we want to completely fill up, i.e. we want to have all the sum of the faces be equal to exactly n. So first, we do the first step, and we first define the DP, the dynamic programming. And so we define DP of x as the number of sequences of dice rolls that add up to x. And then we consider the last dice roll that brings us up to a total sum of n. And if the last dice roll was a 1, then we know that there are DP of n minus 1 ways to achieve n when the last roll is run 1. Note that the dimension in this DP is simply the sum of the dice rolls to that point. So DP of n minus 1 stores the sum, the number of sequences of dice rolls that sum up to n minus 1. So this logically follows, if the last roll was a 1, then we know that there are DP of n minus 1 ways to achieve the sum of n. If the following row is a 1, if the following row is a 2, then we know that there are DP of n minus 2 ways, 2 ways to achieve the sum n. And then this holds for the other cases. It holds for 1, 2, 3, 4, 5, 6. Then we simply get this relation: DP of n equals DP of n minus 1 plus DP of n minus 2 plus DP of n minus 3, and so on, up to DP of n minus 6. And then we can simply compute the answer by running a for loop from 0 to n, and then we can basically compute each value of n by simply looking at the values before it, because at each stage of the for loop, you would have computed all the values. Suppose our for loop is at a point A, then we, at that point, since we are computing the DP values in order, we would have computed all dp of a minus 1, dp of a minus 2, dp of a minus 3, all the way to dp of a minus 6. And then we'll be able to compute dp of a by simply adding up the six previous values. Okay, these are some DP practice, knapsack DP practice problems from USICO. I think you can like go into our Google Drive, and access this PowerPoint. So if you want practice, especially for like the upcoming USICO contest, since it has USICO typically has a lot of DP problems, it'll be probably some good practice. Okay, and I'll move on to another type of DP, and this type of DP is called dynamic programming on ranges. And this is basically when your DP states correspond to every possible range of an array. And for example, a DP on range might be defined by DP of ij is equal to a certain quantity in the range from I to j in the original array. For example, it might be the sum. And you want to think about each range's relationship with other ranges. Typically, you want to like relate it to ranges that are like subsets, subarrays of the range. And you might want to consider like from ij, its relationship with I to j minus 1 and I plus 1 to j. And that's typically how you will compute the values for this. And so here's an example of DP on ranges. Suppose we want to compute the maximum subarray sum with DP on ranges, and we have an array of length n, and you want to find the subarray with the maximum sum. And there's an algorithm called Cadence that solves this. It's a standard algorithm that solves this in linear time, but we won't use it because we want to use DP on ranges. So yeah, I'll just go over the solution now. Our DP array will have dimensions of n by n, where DP of ij is just the sum of the range I to j. And then, so our base cases, the initial cases that we had to compute first is when the range is simply just one thing, one number, and that's fairly logical. DP of ii is just equal to the element at that index. And then in other cases, just find, you compute DP of ij by simply using this formula, DP of ij to j minus 1 plus the element at index j equals DP of ij. And that logically results in the value of DP of ij. And then you can just, in order to compute the matrix in the DP matrix in an efficient way, you can start by, one way is to loop in order of the size of the range. Like if your range, you can loop from ranges of size 1, size 2, size 3, all the way to the size of the original array, which is n, and then compute it based on that. And yeah, that's one way to compute it. And basically after that, the last part of the solution, once you have computed the whole DP array, we still have to answer the original query, and we want to take the maximum among all the values of DP to find the maximum subarray sum. Yeah, this isn't even the most efficient solution, but it shows dynamic programming on ranges. So these are some DP problems, DP on ranges problems you can try later. So DP on trees. It's basically just dynamic programming, but on trees. And typically you want to find the relationship between parents and children, and then you want to calculate your answer through either depth first search, probably depth first search. And typically you compute each answer for a node based on the values of its children. And yeah, So here's an example. So we're giving a tree that's rooted at 0, and it has values assigned to each node, and you want to basically return the sum of the maximum values in the subtree for each node. And basically for every node in the tree, you want to take the maximum value in the subtree of that node, which includes the node itself. You have to always remember that the subtree of a node includes itself, and then add up this value for all the nodes. So like here's the sample input. You have n, and then you have n minus 1 lines containing usually 2 values on each line. Let's call them u and v, and then that usually indicates that it's there's an edge in the tree between nodes to u and v, and then you have n numbers that represent the values of the nodes. And so this might be an input. So it first contains the number of nodes n. There are 5. And then remember that it's typically 1 indexed. And then there are edges between 1 and 2, 1 and 3, 2 and 4, 2 and 5. And you know that there are n minus 1 of them, so there are 4 lines, because this is DP on trees, and trees have n minus 1 edges. And finally, these are the values of the nodes. Remember, it's 1 index, so this is the value of 1, 2, 3, 4, 5. And then we want to find the maximum value of any node in the subtree for each node. And basically, for node 4, it's 4. It's node 5, it's 2, and so on. You can just work out the example by yourself. Yeah. So let's see how we want to do this with DP. So we define DP of I as the maximum value of the subtree of I, and the base cases in this case are the leaf nodes, which if leaf nodes are the nodes in the tree at the very bottom that don't have any children. And for such cases, we store the value of the node in the DP node array and add it to the sum. And the reason we do this is because the maximum value of the node is obviously just of the subtree is obviously just that node, because that's the only node in the subtree. So yeah, and it's also you also add it to the sum. And for the parent nodes, we take the max of all the values of the DP values of the children, and then set DP node to that value, because if you imagine the structure of the subtree, it consists of the node itself and the subtrees of its children. So you can just iterate through the children's subtrees and take the max of the DP values, and also take the max of the value at that node. And yeah, and then you continue to do this, and you can compute all the values using a depth first search. Yeah. So here are some problems for DP on trees. You can try these later. These are pretty good practice for USCO, because USCO, some of the most common topics are dynamic programming, and another super common topic is trees. So this will be very good practice. Now we'll go over a last topic. It's called DP on bit masks. These aren't as common in USCO. They were slightly common back in old gold, but we'll go over them anyway. So DP on bit masks is different from the other types of DP in that the time complexity is way larger, and it's usually n times to the power of n. And typically this means that n can be at most like 20. And this DP utilizes bit masks And just to make sure you guys know what bitmaps are. So bitmaps, they are you can iterate from. Suppose we are our n is 5. We want to iterate from 0 to 2 to the power of 5, and what this represents is each number, if you view it in binary, each digit will be either 0 or 1, and the 0 digits represent n will be like the number of items, right? So the number of things we're considering. So we'll be basically iterating through every possible subset of n, because each when you view it in binary, each digit will be 0 or 1, and 0 represents an item that is not taken, and 1 represents an item that is taken when you view the bits as 0 or 1. So then the transitions also in this DP come from you transition from the subsets of each set, and basically you transition from the sets that contain all of the same elements except for one of them, except that it's missing one of them. And you should see this in the example. So suppose we have n watermelons with a known diameter and weight. Find the smallest difference between the total weight and the total diameter in any set of melons. So here's a typical input format. There's n watermelons, and then this D1, these D's represent diameters, and these W's represent weights, and it gives you the diameter and weights of all the watermelons, of all n of them. And this is a sample. And yeah, and our objective, remember, is to find the smallest difference between the total weight and the total diameter in any set of melons. And you can work this sample by yourself. I'll just go over the solution now. So in order to do DP on bitmass, we define an array DP that has a size of 2 to the power of n, which represents all the different subsets of the n items. In this case, it's all the different subsets of the n watermelons. And just as a useful trick, you should always try to use like bitwise operators like shis. And this expression represents 2 to the power of n. And we define dp of I as the difference between the weight and the diameter of the set, where the ones in the bit set represent that an item element is in the set, like I said earlier. And for instance, suppose we're looking at dp of 5, the binary representation is 101. And this means that elements 1 and 3 are in the array. And note that when we're looking at the binary representation, you have like multiple options to. You can like index the numbers from left to right or right to left, depending on what you want. Typically, it's from right to left. So this first bit, if it's 0, it represents that the element 1 is not in the set. If it's 1, it represents that it is. So in this case, it's 1, and it means that element 1 is in the set. And this is element 3. It's also represented by 1, so that means it's also in the set. And so after that, we run a loop from 1 to 2 to the power of n minus 1. Which goes over all the different subsets. I hope I didn't confuse anyone earlier when I said like run a loop to 2 to the power of n. I actually meant 2 to the power of n minus 1, because 2 to the power of n is not actually like, it has extra bits, and this you run it from 1 to the power of n minus 1. Sometimes you can run it from 0 to the power of n minus 1. Anyway, so for each state, we loop through all the possible states that the current state could have possibly come from, which means that we loop through all the states that have the exact same elements, except that one of the element in the current state is missing. So for instance, if we're trying to calculate 5, which has the bit representation of 101, we would look at the elements 001 and 100 in order to calculate the answer. So then the transition for this DP is simply just you find the subset without an element, and then you add it to the difference between the weight and you add it to the difference between the weight and the diameter of the element that's missing. So for instance, suppose the subset without an element is 100, which is 4. So the element that is missing is 1. So we take the DP value at 4 and add it to the difference between the weight and diameter of watermelon 1. And then we set that as the answer for DP of I. And afterwards, we still have to complete our final objective of finding the minimum of all the possible differences, which is, in this case, you just iterate through all the possible DPIs and just take the minimum of all of them. And then that's simply the answer. So these are some more useful problems, and you can simply do these also as practice. So lastly, I'll just give some tips and tricks for DP. So DP is one of the topics that is learned mostly through practicing, just doing problems. And here are some tips and tricks. When thinking about what dimensions and states your DP has, you should look at one clue is to look at the limits of the problems, especially for like bitset DP, bitmass DPs. If the n is really small, it's like typically a giveaway that it's a bitmass DP. And typically when you're when you calculate your time complexity, it should be within the time limit of typically 100 million. When your dimensions are multiplied together, it will be close to the time limit. So just basically try to guess like what are the dimensions based on that. And some like typically time complexities for DPs are basically the dimensions multiplied together, and then after that multiply by the time of transition for each time. So for instance, if we look at the bitmass DPs, I said that the time complexity was O of n times 2 to the power of n. This is because we have O to the power of n states, and each transition is O of n. If you remember, each transition involves iterating all the typically it involves iterating through each possible subset with only one element missing, and there's O of n of them. So it's an O of n transition multiplied by 2 to the power of n states. Okay, back to the tips. And so our next tip is just to, when coming up with transitions, think about how current state in your DPs differs from the last state and how that state affects your current state in the DP. Yeah, and then when transitions take more than constant time, you should sometimes you can find the minimum or maximum among a certain set of past states, and then this can sometimes speed up your DP. Yeah, like sometimes you have to calculate DP values for you have to use in a transition between suppose DP of I minus 1 and DP of I. Sometimes it's good to like compute supposedly like the prefix maximum of all the elements of DP from 1 to I minus 1, and then you have to use that transition to find DP of I, and that's sometimes a key to lower the time complexity. Yeah, basically this is all I had for the DP presentation today. If you want, you guys can get started with a knapsack DP problem. So this is first one. It's called Fruit Feast, and it's Usico 2015 December contest gold, and it's problem 2 of it. And so you can get started by reading it and thinking about it.